Hi, I welcome you back to the next session on resonance model of benzene. But first of all, I would like to ask you this question. Have you practiced writing Kekule's model of benzene, its acceptability, its introduction, its limitations? I want you to also practice writing these things and build your concept alongside you're watching these lectures. I would also encourage you to join the course on Udemy because Udemy is actually an educational platform. There are much more opportunities there. We can have quizzes, we can have assignments. If you complete the whole stuff, you can get the certificate. I can see how much course have you completed. I can check your assignment and can give reviews. So Udemy is actually a platform that can support our learning. So I would encourage you to join the course on Udemy. So please do revise what is being taught to you in this course. In this session, we are going to start resonance model of benzene. Previously, we have discussed that Kekule was the first person who gave a very good structure and a lot of things were solved. It was solving out many of the problems and everything was doing great, except there were three major flaws in the Kekule's model which led to its unacceptability, and newer models were given attention. So one of the newer model is resonance model of benzene, and it is even accepted till date. That is why the syllabus has asked you to learn about this model. This model is based on the fact that the two canonical structures which were provided by Kekule are under resonance, and there is a hybrid structure out of the two structures. The two structures which were given by Kekule are individually called the canonical forms. This is canonical form number 1 and this is canonical form number 2. So these two canonical forms are under resonance, and there is a formation of hybrid structure which is like the equal half of both of these things. This is similar to the Hindu story on the Narsim avatar of Bhagwan Vishnu. If you have heard of this story, in this the god has taken avatar form where the form is half animal and half human, half lion and the half human, so hybrid. The demon is being killed not in the morning and nor in the night, he is being killed in the evening time, so hybrid of day and night. He is not being killed by the astra or the shastra, he is being killed by the nails of the Bhagwan. He is neither being killed on the earth nor in the sky, he is being killed on the lap of the avatar. He is neither being killed outside the home nor being killed inside the home, he is being killed on the door place itself. So lot of things which were hybrid in this story. So similarly, our resonance model has also shook hand with hybrid nature. The resonance model has stated that you take the two canonical forms and make a hybrid of it. So this is nothing but your resonance model. It also talks about the bond length of the carbon-carbon bond in benzene and says there is no pure double bond and there is also no single bond. Instead, there is partial single and double bond, and the value of all the bond lengths is same, which is 1.39 angstrom. It is the middle value of both the double bond and the single bond, because double bonds are 1.34 angstrom in length and the carbon-carbon single bond is 1.54 angstrom in the length. So the bond in benzene is actually in the mid of these values and the value is 1.39 angstrom. So this was your resonance model. And resonance model said that as the resonance hybrid is more stable as compared to the canonical forms, because it contains the average out of 2, so there is more stability and more uniformity, so it is more stable. So that is how the model is claiming that this is how you can explain the exceptional stability of benzene. And we have also explained the equality of the carbon-carbon bond length in benzene. Alongside explaining all these things, resonance model also talks about a term called resonance energy. Resonance energy is the value of energy through which benzene is more stable as compared to the canonical form. So the definition of resonance energy is nothing but difference in energy between a resonance hybrid and its stable hypothetical contributing structure is called resonance energy. That means the resonance hybrid, the energy of this, and the energy of the hypothetical structure of benzene when compared, it is now considered as a hypothetical situation because this is not the way benzene exists. This is the way it exists. So the difference between these two energies of these two structures is called the resonance energies. This is the definition. Now, is it possible to figure out the exact value of resonance energy of benzene? The answer is yes. It can be found by performing some set of experiments on heat of hydrogenation. Let me explain you how. If you can compare the heat of hydrogenation of cyclohexene and benzene, you can figure out the resonance energy. So what you do in this experiment, please try to follow me. Do not go and read text. I will make you understand each and every point. So there is no need to read the text and waste any time while you can build the concept itself. So once you take cyclohexene is nothing but cyclohexane with one double bond is cyclohexene. So if you make it undergo hydrogenation means addition of hydrogen in the presence of catalyst which is nickel, and the pressure is 1 to 2 atmospheric pressure. So there is a release of energy which is around minus 120 kilojoule per mole. I want you to focus on this particular value itself of the kilojoule value. Forget about the kilocalorie value at this point of time. Forget about this value at all. So this was the energy which was released when hydrogenation was performed for cyclohexene. The reason for release of energy was when hydrogenation happens, there is formation of carbon-hydrogen bond, two carbon-hydrogen bonds. In fact, when the bond is formed, the energy is released. On the other hand, if the bond is broken, the energy has to be supplied. So in this case, two carbon-hydrogen bonds are being formed, although there is breaking of one double bond, but that is compensated by formation of these bonds itself. So finally, minus 120 kilojoule per mole of energy is released. Enthalpy is nothing but heat. Similarly, when the experiment was performed with benzene, this time the pressure was increased because benzene is a stable molecule and it does not react as easily as the cycloalkene. So the answer came out that this process released 209 kilojoule per mole of energy. So in the previous case, the energy release was 120 kilojoule per mole, and in the case of benzene, the energy release was 209 kilojoule per mole. Now, it was expected that when cyclohexene has one double bond and there is release of 120 kilojoule per mole of energy, the benzene contains 3 double bond. So that means there should be a release of roughly around 360 kilojoule per mole energy, but that was expected value. Experimentally, when you see, the energy release was 209. So if you subtract 360 minus 210, if you consider it as 360, consider it as 210, the answer comes out to be 150. So the difference between the expected value and the experimentally observed value is nothing but resonance energy, and the perfect value for this is 150 kilojoule per mole. You can also depict this whole thing in terms of a diagram or you can see a graph where on the y-axis is the energy and on the x-axis are the points of the chemical structures. So at the lowest is your cyclohexane, because benzene is reduced to cyclohexane and cyclohexane is also reduced to cyclohexane, and that has the most stable form because all the energy has been released until now. So cyclohexane is 120 kilojoule up as compared to cyclohexane. So the level is up. More up is the hypothetical structure of benzene, where it was expected that 360 kilojoule of energy should be released when benzene is converted to cyclohexane. But benzene actually lies in the mid of these 2 points, somewhere in the middle. The point is 210 or 209 kilojoule per mole, whatever way you want to write. And the difference between the actual benzene and the benzene's hypothetical structure, the difference is 150 kilojoule per mole. So this gap itself is called the resonance energy of benzene. Actually, there is inverse relationship between energy and stability. Anything which will be high in energy would be more unstable, and anything which would be in lower energy level would be more stable as compared to the previous one. So there is a difference of 150 kilojoule per mole of energy. So that means benzene 150 kilojoule per mole of energy more stable as compared to the hypothetical structure. So this is how you can figure out the resonance energy in real. So if somebody asks you how much stable is benzene then as compared to other alkenes, so the value is going to be 150 kilojoule per mole. If somebody asks you what is the resonance energy of benzene, so the answer would be this. So this was your resonance model of benzene. I hope you were able to get a clear picture of what resonance model has to say, and you got aware of the resonance energy concept. You got the value also. You got how to better explain the things in terms of graph. So this was resonance model. There is one more interesting model on benzene, and that is molecular orbital model, and that is more like a pictorial depiction of the benzene structure. So stay tuned for learning that model also. So see you in the next session.